Now today we're going to begin our chapter on inverses. As we talk about inverses, we're going to start talking about something called a one-to-one relationship. And this sounds pretty darn familiar. One-to-one relationship. Every y has only one x. Now we've heard that before. But when we heard it before, it was every x has only one y, and that was a function. So we're kind of switching the roles of the x and the y around here. And when we do that, that's called a one-to-one relationship. So the y's never occur twice. One-to-one relationship passes the horizontal line test. So if we have something like this, every y has only one x value. The y value of 4, for example, has this x value right here. And the y value of 4 has no other x values. So it passes the horizontal line test. A horizontal line is only going to touch a one-to-one relationship at most at one point. Now this isn't a function because it fails the vertical line test, but it is a one-to-one relationship because it passes the horizontal line test. And if we take the inverse, and we're going to talk about how to do that, if we take the inverse of a one-to-one, you're going to get a function. So the inverses of one-to-ones are functions, and the inverses of functions are one-to-ones. Sometimes something could be both a one-to-one and a function. What about like cube root of x? If I drew cube root of x, would that pass the horizontal line test? Shouldn't have made that look so horizontal up there. Actually, should have climbed a little bit. Does that pass the horizontal line test? Sure it does. Does it pass the vertical line test? Yes, it does. So something can be both. But the inverse of a one-to-one is a function, and I do believe that the converse of that is true. Now, if a relationship, this one-to-one relationship, has a domain of A, set of numbers, we'll call it A, and a range, a set of numbers, which we'll call B, then the inverse is going to switch the domain and the range around. So we've got a relationship that has a point 3, -7, -5, +2. Name points that are on the inverse. Well, we've got to switch the domain and the range. Now 3 was in the domain while 7 was in the range, so I better switch those around. A point on the inverse would be -7, +3, because the domain and range, the set of x's and the set of y's, have reversed roles. Same thing here for this point. We got to switch the x and the y. We've got a 2. We've got a -5. So those are on the inverses of each other. And inverses are reflections over the line y equals x. Well, let's see. Let me in green plot these 2 points up here. 3, 1, 2, oh, I better come down here. 3, -7, 1, 2, 3, 4, 5, 6, 7. And I would like to plot -5, +2. -1, 2, 3, 4, 5, +2. Now I'm going to graph their inverses. I'm going to graph -7 and +3. I'm going to graph 2 and -5. Now, are those reflections over the line y equals x. In other words, if I drew a line from a point to its inverse, do those look like reflections? Does it look like if I folded this paper on this y equals x that those guys ought to match up? What about these guys? Probably should have picked some things that were a little further apart. But yeah, those look like they are reflections over y equals x. All right. Now, let's forget about those points for a second. But if I had some, maybe function that looked like this. Its inverse would be the reflection over y equals x. Let's see how well I can do this. Something like that. So they would be reflections. If you look at the graphs of two, let's see, a couple of relations here. They would be reflections over the line y equals x. And if they are inverses. And if they are not reflections over y equals x, they are not inverses of each other. Now, method for finding inverses. You have found inverses before. And when you have found inverses, method for finding inverses. We're given this function right here. We're supposed to find y inverse. This does not mean 1 over y. This means the inverse of y. All right, what we're going to do is we're going to start with our original equation, and we're just going to switch the x's and y's. So instead of y equals, I'm going to have an x equals 6y squared plus 8. So switch the x's and y's because domain and range switch on the inverses. Now let's solve for y. I think I would subtract 8 from each side. I do believe I divide by 6. And I believe I would square root both sides. And I think I would have to remember that if y squared is equal to this thing, then y is either the positive or the negative square root of x minus 8 over 6. And now that I've solved for y, what I've actually found, I haven't found y, I have found the inverse of our original y function. Okay, that is the inverse of the original y function. Okay, so y was equal to this. Y inverse is equal to this guy. Now there are going to be times when it's really, really hard to find the inverse. And now don't even write any of the things I'm about to write. Let's see, I'm going to switch the x's and y's. Okay, now try to get y all by itself. Well, it's just not going to happen. So we can't find the inverse. But what if we can't find the inverse? But we're asked to find the inverse evaluated at 0. Well, if we can't find the inverse, how are we going to evaluate it anywhere? That's kind of crazy talk. Well, here's what I know. I know that f inverse of 0 is what I'm looking for, and I have no clue what it's equal to. But if f inverse of 0 is equal to I don't know, that means that f of I don't know is equal to 0. In order to figure out what this question, the value of this question mark is, what do you put in for x so that you get 0? Can you think of any number that you could put in for x so that the result of this whole thing is 0? And if you're saying that f of 1 is equal to 0, then you have found that f inverse of 0 is equal to 1. That's the method we're going to use to evaluate inverses when we can't even find them. Okay? We write what the question is, then we write the inverse of that question. We figure out what that unknown x value is, because that unknown x value becomes the value that we're looking for. Now that's probably going to take some practice, and we're going to see that come up again shortly. Like right now. Katz's theorem of inverses. We know that if f of a is equal to b, then f inverse of b is equal to a. Okay, we know that. Now what's also true, but is not as widely known, is that if f primed of a is equal to w, if we take the derivative at a of the function, we get a value w, then the inverse, the derivative of the inverse evaluated at b is equal to 1 over w. It's equal to the reciprocal. So we got this function. We can't find the inverse. We're asked to find f inverse of 1. Okay, now I call this the horseshoe method. And the horseshoe method says this. The horseshoe method, the way I would start this is, here's my question. Find f inverse of 1. Okay. F inverse primed of 1. So what I'm going to start with is, I'm going to start just with f inverse of 1. I'm not going to focus on the derivative quite yet. And I'm going to end by finding what I'm looking for. F inverse primed of 1. Okay? So we start with f inverse. We end our horseshoe down here and set this up like this, and I think you'll catch on. Now f inverse of 1, I have no idea what it is because I can't find the inverse. But let's use the method that we just had. If f inverse of 1 equals question mark, f of question mark is equal to 1. So I should be able to figure out what question mark is. What are you going to put in? What are you going to put in the place of x so that you get 1 as a result? Now, it's got to be an easy number. It's got to be something that's pretty easy to check. Now, I think from what we understand about secant, that's 1 over cosine. I think that if I put a 0 in for x, I'm going to get 0. Secant of 0, 1 over the cosine of 0 is 1. So I realize The question mark has a value of 0. Now the horseshoe. Now we're coming back this way. And down here, everything has to do with the derivative. I got to find f primed of 0, f primed of that value I've just found. Now let's take a look at this. If f of x equals negative 3x plus the secant of x, then the derivative f primed of x equals negative 3 plus secant x tan x. And f primed of 0 is negative 3 plus secant of 0, which we know is 1, times tan of 0, which we know to be 0. So f primed of 0 is equal to negative 3. Now, if I know this is negative 3, then what's the derivative of the inverse? Well, Katz's theorem of inverses tells us that if I can find the derivative at A, the derivative of the inverse at B is going to be the reciprocal. So if this is negative 3, doesn't this have to be the reciprocal? Negative 1/3. Oh, that's going to take some practice. Well, let's practice it one more time. I've got this function here. Going to be pretty tough to find the inverse. Maybe I could do it, but we're going to use the horseshoe method. I've got to find f inverse of 1.5, f inverse primed of 1.5. So I'm going to start by finding f inverse of 1.5. I will end by finding f inverse primed of 1.5. Okay. This is equal to question mark. So f of question mark equals 1.5. What do you put in for x? So that this thing has a value of 1.5. Well, this is 2.5, so this better be negative 1, huh? What do you put in for x so that this thing to the 5th power is negative 1? Are you thinking six minus 7 is negative 1. Negative 1 to the 5th is negative 1 plus 2.5 is 1.5. Yeah, I think we got it. Now let's bend that horseshoe around and let's start dealing with derivative. What is f primed of 6? Well, here's f of x up here. Let's find the derivative. It looks like a chain rule problem. F primed of x. 5. Don't mess with the inner function. To the 4th power times the derivative of what's inside. So f primed of 6. 5. 6 minus 7 to the 4th times 1. You agree with that? And now, to answer our question, what is the derivative of the inverse? It's the reciprocal. Now that seemed a little bit easier. And the more we practice this method, the better off we're going to be on it. So, with that in mind, let's practice.